question 11.3, we deal with the ideal gas law. So this is the relationship between pressure, volume, the number of moles, and temperature. So it combines all the other gas laws into the equation PV equals nRT. All right, so in this equation, P is pressure in atmospheres. V is volume, which is given in liters. N is the number of moles. R is the gas constant, which is always going to be the same for each time. And T is the temperature in Kelvin. All right, so this law assumes several things. So it assumes that the molecules do not interact with each other, that the combined volume of the molecules is much smaller than the total volume. All right, so when we use this, we want to write all units, okay? So, and the units will help you determine where to put each number. All right, so once again, the equation, the ideal gas law, PV equals nRT. R is the gas constant, and this is found experimentally, and it will always be 0.08206, or you can use, if you would like, 0.0821 liters atmosphere per a mole Kelvin. And the units are the way they are, just so that they cancel with the rest of the variables in the equation. All right, so we can, if you would like to, you can write these down. You can solve for each variable individually. So if we take and want to solve for the pressure, this would be the relationship. The volume is this relationship right here, temperature, and the number of moles. Or you can conversely just plug in the numbers when you're given them in the problem and then solve for it. And then when we solve these, we multiply all the numbers on the top and then divide by the numbers on the bottom. If there is more than one number on the bottom, you may need to use parentheses in your calculator when you divide. So let's do some examples. So for this one, what is the pressure of 5 moles of gas at 373 degrees Kelvin in a 2-liter container? All right, so we're given many different things. So we have 5 moles here. So the number of moles is 5. We know that the temperature is 373 degrees Kelvin. And we know that we have a vessel that is 2 liters. So our volume will be 2 liters. All right, if we plug this into our equation here, so P equals N, so we want our 5 moles times R, which is 0.08206. liters per an atmosphere mole Kelvin, times our temperature, which is 373 K. Now we divide this entire thing by our volume, which is 2 liters. Right? Let's go ahead and see if our units should cancel, our moles will cancel, Kelvin cancels. So we're left just with the units of atmospheres, right? Which is what we want. And if we actually calculate this, I have not done this yet, 0.08206 times 373 divided by 2, we end up getting 77 atmospheres is our pressure, okay? So that's solving for pressure. Now, if you would like to, and you did not have this, and you just had PV equals nRT, you could just plug it in, right? So we would know that we don't know our pressure, but our volume would be 2 liters. Then we would have this same thing at the top, 5 moles. This is what we did in class, times 0.08206 liters atmosphere per mole Kelvin. All right, and times 373 K. So you could solve it this way, and then we would end up getting the same answer. Okay, so let's try now calculating volume. All right, so the expression for volume is nRT over P. All right, so let's look and see what we have here. So what is the volume of 0.15 moles of neon gas at 100 degrees K and 1.25 atmospheres? So the moles will be 0.15. The temperature is 100 K, and the pressure is 1.5 atmospheres. All right. So if we plug this in, we know our N is 0.15 moles times R, which is 0.08206 liters atmosphere per a mole Kelvin. T is 100 K. And then lastly, our pressure is 1.5 atmospheres. Okay, if we calculate this, we take 0.15 times 0.08206 times 100 divided by 1.5, and we end up getting 0.82. And then what are the units here? They're going to be liters, right? So if we cancel our units here, you can see that we're left with liters. So that is the answer for that one. All right. Next example, calculating temperature. So if we rearrange the equation for temperature, that's what it looks like right here. So this question says, what is the temperature of a hot air balloon with, well, this is a lot, 2.5 million liters of air at 0.75 atmospheres and with 61,000 moles of air. So this is a hot air balloon, so the numbers are going to be really big, all right? So we know the pressure is going to be 0.75 atmospheres. The volume is going to be 2 2,500,000 liters, right? And the number of moles is 61,000. This is going to be a lot. So let's go ahead and put this in. So our pressure is 0.75 atmospheres times V, which is 2,500,000 liters, divided by the number of moles. We have 61,000 moles. So many moles. All right, and our gas constant, which is the same as ever, 0.08206 liters atmosphere per a mole Kelvin. Let's cancel out the units we can, and we are left with Kelvin, which is good because that is what we want. Calculating this. Right, dividing by 61,000. If you do this dividing all in one step, you would have to put it in parentheses, or you can, all right, so we end up getting that this is going to be 375 degrees Kelvin, all right, hot. So that's why we call it a hot air balloon. All right, one more example. Let's go ahead and calculate the moles. So calculating the moles, this is the expression we get, that we have the moles equals PV over TR. All right, we're going to look at the example of a car tire again. So we're going to ask how many moles in a car tire at 300 degrees Kelvin, that's our temperature, with a pressure of 2.4 atmospheres, that's our pressure, and a volume of 16.4 liters. So 16.4 liters, all right? So plugging in our numbers, we have 2.4 atmospheres on the top times our volume, which is 16.4 liters. I actually looked these up. These are close to what they are. The temperature is 300 K, all right, and our R is 0.08206 liters atmosphere per a mole Kelvin. All right, doing this calculation, 2.4 times 16.4 divided by 300 divided by 0.08206. And we end up getting that there are 1.6 moles of air in this car tire. All right, and that is it for